When we talk about chemicals used to passivate, there are a number of acids that can be utilized. We did a series of testing to compare these processes, including just cleaning only with oxidizing. We used phosphoric acid. We also used nitric acid and citric acid. And when we evaluate these processes, we utilize the chrome to iron ratio testing that gives us a quantitative method to compare the quality of the passive film generated by these different processes. For instance, cleaning and oxidizing only will give us somewhere in the range of 1 to 1.2 chrome to iron ratio. If we electropolish or if we passivate with phosphoric acid, we're in the range of 1.2 to 1.4 chrome to iron ratio. With nitric being the standard, it's approximately 1.5 chrome to iron ratio. The results that we get from citric are as high as 1.8 to 2.0. So you can see there's a distinct difference in each of these process types with the quality of the passive film that we receive. As a guide, the quality of the passive film is based on the chromium content, but we also do corrosion rate testing. And just to give you an idea, the difference between a surface that has a 1 to 1.2 chrome to iron ratio when compared to the level of nitric at 1.5, nitric has approximately 2 times the corrosion resistance. That passive film produced by nitric has 2 times the corrosion resistance of the mill finish that's at 1 to 1.2. Compared to citric acid at 1.8 to 2.0 is double the corrosion resistance of nitric. So compared to a mill finish, a citric acid highly passivated surface is going to have up to 4 times the corrosion resistance of a mill finish. So it's very important that we utilize this kind of testing to compare these different processes to give us ideas on what is the quality of the passive film that's generated. In this movie we're about to see, we're going to see an EDTA molecule that is utilized to create a bond with a metal ion. You can see the chelation process occur, and that renders it non-reactive and allows the element to be processed out of the system. So the next slide talks about the effects of temperature and the use of citric acid as the passivation chemistries. One of the things that you'll note is that the effectiveness of these processes depend on the conditions that they're utilized. So for instance, with citric acid, if we use it at ambient, the results are nothing better than cleaning. We see that the chrome to iron ratio is about 1.2 for cleaning only, followed by oxidation. And the citric acid at ambient only gets us a chrome to iron ratio of 1.2. But if we use the citric acid solution at a temperature of 60 degrees C, we then get results equal to nitric. They're both at around 1.5 chrome to iron ratio. Further, if we use the citric acid at 80 degrees C, we get the chrome to iron ratio up to 1.8 or as high as 2.0. So the conditions that we utilize these chemistries are critical to their success. For instance, ASTM A380 claims that citric acid is nothing better than a cleaner because at the time it was written, they used citric acid at ambient and compared nitric and citric at ambient. So it's very important that these processes are used at the right conditions. The next series of tests has to do with using citric acid at 60 degrees C, but at different time frames. So one of the things that's important here is to run the citric acid passivation process long enough. For instance, we have a competitive product company that sells citric acid as a passivator for 10 minutes. When we test at 10 minutes, what we see is it's nothing better than cleaning again. It's about 1.2 chrome to iron ratio. But if we run it for 30 minutes, we get a little bit better, but it's really not good enough. It's still only about 1.3. If we run it for an hour, we finally get to the equivalence of nitric acid at 1.5. So we know we have to run at least a minimum of 1 hour. But if we run for 2 hours, we get to 1.8 chrome to iron ratio. If we continue and we run it till 4 hours, we still only have 1.8 chrome to iron ratio. So the important aspect here is that citric acid doesn't degrade the surface or doesn't make it any better by running extra long periods of time. So it's why we run for a minimum of 2 hours, typically in the 2 to 3 hour range, to reach the highest level of passivation. But if you run it at shorter periods of time, you don't get the benefit that passivation can give to us from a corrosion resistance standpoint.